Okay, so what we're going to be talking about today is the idea of a potential energy. Previously, up until this point, we've been discussing work, some force dotted with a displacement, or Fx cosine theta, and relating that to an energy, and specifically a kinetic energy, so a 1/2 mv squared. We were looking at force displacement graphs and saying, look, the area under the curve, that is the amount of work that is done, and we can equate that to some change in kinetic energy. Everything went through kinetic energy. But while kinetic energy is the energy of motion, it's not the only energy that exists. We have another form of energy, potential energy. And potential energy is really an umbrella term because there are many different types of potential energies that exist. We're going to be discussing two of them within this unit. We're going to be discussing gravitational potential energy and then spring or an elastic potential energy a little bit later on. But that's not the only kinds. You can get all sorts of different potential energies out there. But that's what we're going to be discussing in this classroom. Okay? Now, when we talk about potential energy, what we're really talking about is the energy of position. Your potential energy is entirely based off of your position. That's what matters. And this is kind of weird, but our symbol that we're going to use for potential energy in the world of physics is actually a capital U. I know that doesn't make a lick of sense, but we use a capital U in physics. Now, between you and me and everybody out there in the world, when nobody's looking, I just write PE for potential energy. But technically speaking, the letter U is what we use there. I think it goes back to the idea that momentum is with a P and pressure is with a P, and so is power is with a P. So why would I say potential energy? Oh, that's too many P's. We'll just U is what we use, but if you use PE, nobody's going to come and get you, okay? But it really is the energy of position. In potential energy, it involves some physical object inside of a field. And what do we mean by a field? That's kind of a weird thing, because like when you watch a movie, it's like activate force fields, and then like things come up, right? That's not what we're talking about when we say fields. When we say fields, what we're representing or what we're talking about is something like a gravitational field. There is gravity all throughout the volume we're existing in. There's gravity here, there's gravity here, there's gravity here, there's gravity everywhere. That, while we just call it gravity, if we wanted to be more formal about it, we would call it a gravitational field. Because when we put an object in that gravitational field, a force is felt by an object. So when you hear the term force field, gravity is technically like a force field. Because when you put an object in a gravitational field, it experiences a force, a weight acting on that object. If we put an object in a field, like this water bottle, this would have a potential energy. It is an object, and we place it in the field. That is a potential energy. If I get rid of the object, though, there is still something there in this space. It's no longer a potential energy. It is referred to as a potential. Think of it this way. If I took the classic bowling ball I have stashed next to my desk for some weird reason, if I put it above your head, it would have a potential energy. I could let go of the bowling ball, and it would change that energy into kinetic energy as it falls to the ground. Like, we'll talk about that in a conservation video. But, like, this has some potential energy. If I get rid of the bowling ball, there's still the potential for me to put it above your head, but there's nothing there that has that energy. Potential energy, potential. Potential energy, potential. Okay? They are different. That is a very subtle, fundamental difference in the world of physics, that a potential and a potential energy are different things. A potential energy has to have an object there. That object has that energy. But the space itself, due to the field, has a potential. So they're slightly different, but it's important to keep that in mind, okay? You don't want to just accidentally slip one term in for the other, and hopefully I won't do that either while we're talking here, okay? So that's what we're talking about for potential energies. We're talking about putting an object at a certain position, sometimes in a field, and with springs just sometimes, on an object, okay? For our first potential energy we're talking about, we are going to talk about a gravitational potential energy. We are going to think about how if we put an object in this gravitational field, how will that object store energy? So we're going to use as our symbol for gravitational potential energy that capital U, but then we're going to subscript it with a little g. That's the same g we used earlier in the year to say like gravity g 9.8 meters per second squared. But this is just, look, it's a potential energy for gravity. And if we think about, if I did put an object above your head, hopefully not to crush your skull and turn it into a watermelon, putting a bowling ball above your head is a lot different than putting a tiny piece of plastic, right? Because the masses are different. Bowling ball has a lot more mass than a tiny piece of plastic. So the mass influences the gravitational energy. As we have more mass, we should have more gravitational potential energy. There's also a difference between if I take a mass and put it just like a tiny little bit above your head versus I go to the top of the Empire State Building and drop the bowling ball off it. Whoever's beneath that will not have a fun day or existence. The height matters as well for gravitational potential energy. So for our equation, we have mass that influences this energy. We have a height that influences energy. And, well, when we think about this, gravity has to implement something here. If I have more gravity, there's more of this pull, more of this field acting down on our objects or inward to the center of the object. That is going to influence. So our equation for gravitational potential energy, UG, is going to equal a mass multiplied by gravity multiplied by some h, some height in this case. That is our equation for gravitational potential energy. Now there is a very important thing here to think about, and it has to do with this h, this height, so to speak. That h is dependent on a reference position. And what do we mean by a reference position? Well, let's talk about this. We are right now standing and sitting in a classroom. How high are we above this floor? Well, we're not. We're like sitting. Our feet are on the floor. 0. But how high are we above the ground? For those of you who aren't here, we're on the 2nd floor of this building. 3rd if you're like take the hillside into effect, because the basement's actually the ground level, right? So we're like 30 some feet up. Wait a second, didn't I just say we're like standing on the floor? We're 0 feet up? That's a reference level. What are you measuring this height with respect to? The floor? The ground outside? The ceiling? Depending on what your reference position is, this height, this h value, might be different. And that's what we're going to take a look at in this example right now. In this example for gravitational potential energy, we have a bookshelf here. And speaking of bookshelves, the greatest bookshelf, in my opinion, is what is known as the IKEA Billy bookshelf. Since 1979, they have sold so many of these that they've equated it to being about one bookshelf is sold every 5 seconds worldwide, which is another bookshelf sold. Anyways, on this bookshelf, we have a book. So we've got a 1.5 kilogram textbook right here. This is the mass. And each shelf is 0.55 meters apart. So this is 0.55. The next gap is 0.55. The next one's 0.55, etc., etc. What we would like to do is to calculate gravitational potential energies, MGH, relative to 3 different positions. So to start, let's do this relative to the floor. So our floor is down here. We know our equation for gravitational potential energy is a mass times gravity times some height. Okay, put height in quotes because it's really some distance there. Well, we know our mass is 1.5. We know gravity is 9.8. Let's try to figure out this h. Well, our floor is the reference position. So how high are we above the floor? Well, this is 0.55 plus 0.55, so that's 1.1. And then we go up another 0.55, 0.55, so that should be 2.2 for our total height. This entire distance should be 2.2 meters. So we can just say here that UG equals the mass, 1.5, times gravity, 9.8, multiplied by this height, 2.2. When we multiply all that together, we're going to get a number. It's going to be in joules because this is still an energy. So 1.5 times 9.8 times 2.2 gives us 32.34, that's a 3 right there, joules. And that's nothing too crazy. We know the mass, we know gravity, we just need to get this height relative to a reference position. When we do this again, we're going to do this relative now to the 6th shelf. So before, this is the 1st, 2nd, 3rd, 4th shelf. Now we're going to do it relative to the 6th shelf up here in pink. It's going to be the same equation. UG equals MGH. We're still going to have mass of 1.5. Gravity's still going to be 9.8. But what is the height going to be now? Well, we're only 2 shelves off. 1, 2. So that height, h, should be 1.1. Our height here, though, because our reference position is above us and we are underneath it, our height is going to be a negative value. You don't have the energy yet to get up there. You've already lost it, so to speak. You've fallen down that bit. So you're already in debt. You're already negative. So when we go and put this UG back in, we're going to get 1.5 times 9.8 times negative 1.1 meters. Rushing this calculation, we should get 16.17 joules. And don't forget, this is a negative because the negative on the 1.1. Okay, and then let's try this last one here. Now we're going to go relative to the 4th shelf. And that 4th shelf is actually where the book is sitting. The book is on the 4th shelf. So we still have the same equation. UG equals MGH. But if we're on the 4th shelf, how much higher or lower are we from that shelf? Well, if we're on it, there is no difference in height. Our height here equals 0. So that gravitational potential energy equals 0 as well. Okay? And technically that is joules. Now, a question that was asked here that we took a little bit of time to pause and talk about was this idea of why isn't that G in gravity negative? Remember, we've only considered that G to be negative during projectile motion, and that's just because we call down negative. Really, gravity is 9.8, and then when it's a vector or you care about things for a vector analysis, you assign it a positive and negative direction. In our case here, we don't care about that. Our potential energy will be a scalar quantity, and the only thing that matters is this h value our relative position. Okay? So hopefully this idea of gravitational potential energy makes some sense for you. It's really just one equation, mgh. The big kicker to it is that H positive, negative, or 0, depending on what you're measuring relative to. So be careful about that. Watch your negative signs. And until next time, we are finished here. Adios, and take it easy.